Hello, and welcome to Exponential Functions, Patterns of Growth and Decay. Okay, so we're going to kind of go with an overview of what we might find here in exponential functions, patterns of growth and decay. So a basic exponential function can be written in the form f of x equals a times b to the x, where a and b are real numbers. A is not 0, b is greater than 0, and b is not equal to 1. The constant b is called the base of an exponential function. All right, so the base b is going to tell us by how much it's growing, and it's a rate of change. So the number of ants at a picnic is growing rapidly. Okay, doesn't tell us anything really helpful. At 11 a.m., 5 ants find the picnic. Each hour after 11 a.m., 3 times as many ants have found the picnic. Not 3 more ants, but 3 times as many. Let A of h represent the number of ants at the picnic h hours after 11 a.m. So what this tells us is start at 11 a.m. And once we know that, we know that 5 ants is our starting value. So this represents the A in the formula. And now over here, each hour, let me underline the each as well, each hour, 3 times as many ants. This will be the B in the formula. And so if we put these two ideas together, we find that the number of ants h hours after 11 a.m. is 5 multiplied by 3 to the h hours. The A of h, the little h in parentheses, tells me what my variable should be. 3 times as many, it's what I'm multiplying repeatedly, and that's what an exponent is. It's repeated multiplication, and I start with 5. So estimate numerically when 11,000 ants will be at the picnic. Anytime it says estimate, we're going to just try a couple values. What happens when we have 5 hours? This is 5 times 3 to the 5th. That's not very many at all. So maybe, I'm going to pull that back, maybe we'll go with 8 hours later. Well, that's 32,000. So we know that it must be somewhere between hours 5 and 8. And it looks like probably hour 7 would be our best bet. Let's see what 7 gives us. Because I'm estimating, this is completely, I'm just guessing and checking, all right? 10,935 ants. So about 7 hours later, 7 hours after 11 a.m., this is 6 p.m. About 7 hours later, there will be nearly 11,000 ants. Whoops, getting just too carried away with my ones and my zeros. I literally estimated. I made a couple guesses, adjusted from there. We're going to find out more about how we can find these exactly later, but as far as estimate, we're going to leave it there. Okay, how many ants, so find the output, at 11 p.m. p.m., that's 12 hours later. Tells me that my h value is 12. So I would like A of 12, which is 5 times 3 to the 12th. And I can do it either way. I could put the 12 inside the parentheses or outside the parentheses. As long as it's only going with the 3, it's going to be okay. These little ants are going to carry you away. There are 2 million 657,205 ants. If you have a 12-hour picnic like we are known to do here in southern New Mexico, we love our cookouts. Looking at number 2, let's keep in mind that we're going to be using our exponential functions. And let's read the problem here. A certain bacteria will double every 15 minutes. If a sample starts with 3 bacteria, find the following. All right, we're starting with 3 bacteria, so our A equals 3. Double every 15 minutes. So this is a little challenging. Times 2, but this, I don't know, let's see. Find an equation for a model of the number of bacteria after H hours. In terms of H hours, we start with 3 and it doubles, but it's not doubles every hour, right? Let's work on this finding H. This will double 4 times every hour, right? Because 15 minutes happens 4 times. And since 4 times happens every hour, hour is our number of units, this will be a 4H. All right, so 3 times 2 to the 4H. Let's put an equal sign so we can tell these apart. Well, we might find that sometimes the number of bacteria or whatever problem we're working on is easier if we change our units. If we had n 15-minute intervals, well, this would just be n. It doubles every 15 minutes, every n. Because our unit of measurement of time in part A was hours, and that's not the same unit of time that we measure in the original problem, we had to convert our exponent to use it, and that was a 4H. Since our n is given in the same intervals, in the same time periods as our original problem, there's no need to convert. So using either model, after 5 hours, I could use a B of H equals 5. Using hours, a B of 5 is 3 times 2 to the 4 times 5. I'm going to put that in parentheses. 3 times 2 to the 20th. Ooh. So that's 3 times 2 to the 20th. That is 3,145,728. Whereas if I chose 5 hours is 20 15-minute increments. So is an n value of 20 if I found B of 20. Notice it's the exact same answer because we eventually get to the same thing. And that's the important part. Whether you measure in 5-minute increments or you measure in hours or even measure in parts of a day, as long as the same measurement will come out in the same, for the same number, using either model, using different time values, it's going to work out for you all right. All right, so this is when our doubling or tripling or multiplying by takes less time than our units. And here we're going to go for more time than our units, I believe. Let's take a look. An isotope of hydrogen, H3, has a half-life of about 4,500 days. What this means is after 4,500 days, half the substance remains. $4,500 days. This is our unit of time. We're looking at groups of 4,500 days. That's an odd one, isn't it? Find an equation for the model of the amount of H3 remaining from a sample of 500 atoms. So just in general, we know that This is hydrogen. Let's go with H of D for days. It's at least given to us in days, so I'm going to use a D. We start with 500. And we know half is remaining after 4,500 days. So if I just had 1 day, it wouldn't give me a half, right? I would have to take the number of days, divide by 4,500. So that when I finally get, if I'm at day 4,000, right, it's a partial half of the half. But when I get to day 4,500 and I put it in for D, this will be a 1. I'll have half to the 1 first power is 1/2 times 500 is 250. So when day 4,500 hits, that's when I get the 1/2. And that's what I have to check to make sure my model is good. So in order to estimate the amount of hydrogen-3 remaining after 50 years, I'm going to give an approximate number of days. There are 365.25 days in a year that allows us to adjust for leap year throughout these 50 years. 50 years is approximately 18,262.5 days. And we know it's not 0.5, but close enough is good enough. So the number of hydrogen atoms after this many days and I'm going to use the 0.5 is a 500 times 1/2 to the 18,262.5 divided by 4,500. I'm going to put that in parentheses. This is what it'll look like on the calculator. 500 parentheses 1/2 to the power of, now mine shows an exponent, but not all calculators will do that. You might see the caret itself. So I'm using parentheses. 18,262.5 divided by our 4,500, because that's how many days it takes to double. We'll get about 30 atoms remaining. And that's not right. That is right. Because of the days and the years, it's a lot of time, right? 50 years is way past 4,500 days. So it's way past the halfway mark. So don't have my doubts. We did it correctly. Now, it seems like maybe this could be hard, this whole exponential thing. How do we know whether we divide? How do we know whether we multiply? We practice. But really, when it comes down to it, this model that we have, and I'm going to put it down here, y equals a times b to the x. A is always the initial value. So when x is 0, we get a out. So it's the y-intercept. It's how many ants we start with. It's how many atoms we start with. It's whatever it is that we're working on. And b is called the base multiplier. We usually call it just the base, but I like the full name, the base multiplier. It's the amount we multiply by. To get the next value. So let's take a look here. See how in example 1, we want to find exponential models of the given data. We're going to call this one f of x. We start x value of 0. My f of x is 20. This tells me my a is 20. And then I ask myself, what do I do? What do I multiply 20 by to get 60? And it looks like that's times 3. 60 times 3 is 180. Times 3 is 540. We're multiplying by 3 every time. That's it. That's how hard you have to work when you're given a table of values to find our model. Again, we have an f of x. Our a value is 25. But what do we multiply by each time? I have no idea. None whatsoever. What do we multiply by? I don't know, but check it out. If we divide 30 divided by 25, we get 1.2. What that means is 25 times 1.2 will make 30. What if we multiply 30 times 1.2? 36. And I bet you can guess what happens to 36 when we multiply by 1.2. We get that 43.2. So you might not be able to see the pattern going forward. I don't know what I multiply to get this. I have no idea. But I can divide, and 30 divided by 25 equals 1.2. So now I check each one of these, and I see that I multiply by 1.2 each time. That will be my B value. All right, so remember, multiplication and division, they're opposite operations. So if multiplication doesn't occur to you, you can use division to find out where everything's headed. One more problem. F of x. We know that we start here at 3200. That's where the x value of 0 is. It has nothing to do with this being the first value in our table. It's because of the x value of 0. My a value is 3200. Now, to get from one to the next, I definitely divide. And my dogs feel like coming in to bark here real quick. So I want to know what I divide by. And I know that 3200 divided by 800 gives me 4, right? 3200 divided by 800 gives me 4, but more importantly, 3200 divided by 4 gives me 800. And if I divide that by 4, I get 200. And if I divide by 4 again, I'll get 50. And so each time I'm dividing by 4. But remember, this is a base multiplier. Base multiplier. So how do I write multiplication when I'm trying to divide by 4? That's a fraction, right? Dividing by 4 is the same as multiplying by 1/4. If you think of the b as being your multiplier, you will always change a division into multiplication form. All right, that's it for this video. Thanks for listening.